Okay, good morning fellas. Now today we're moving on to part 3 of our little series on geometric sequences, and here we want to talk about finding the nth term, that means any term, of a geometric sequence, which I've abbreviated to GS, not to be confused with geometric series. Okay, what we need to know is this formula. The general term of a geometric sequence is given by A times R, which you raise to the power of n minus 1. Okay? That's our formula that will enable us to do these sorts of things. We can use it to find a rule for a sequence of numbers. So if we've got a string of numbers, we'll be able to find a rule that complies with that template. And then go on and use that rule to find any term in a geometric sequence. So that's pretty well what it's all about. Okay, how this comes about is really quite straightforward. If we think about a geometric sequence as comprising a first term, we know that the second term is found by
the rule substitute.
Okay, well we don't have a formula yet.
T3 over T2, whatever.
What we do to get to the second term is multiply the first term by the common ratio, don't we? Okay, so we could call that AR. Alright, so that's our first term, T1, T2, second term, and our third term is going to be A times R again, isn't it? So each successive term is found by multiplying the previous term by R. So R times R is R squared. Sorry, I made a mistake there. So that would be our third term. And our fourth term would be AR to the power of 3. Okay? So now maybe you can see a connection between the term number and the power of R. Notice that for the fourth term, the power of R is 3. For the third term, it is 2. For the second term, it's an invisible 1. And technically here, it would be R raised to the power of 0, right? Which is anything to the power of 0 is 1. So we'll just leave it there. So you can see probably how that comes about, just in that very brief demonstration. Okay? Now, our first job is to find a rule for the sequence given by, maybe I could have said Tn equals, to indicate it's a geometric sequence, or a sequence anyway, would indicate it's geometric. And so that's quite straightforward. We go back to our formula, our parent formula, our template if you like, that describes any geometric sequence. And again, it's a case of finding out values for the relevant pronumerals. I can find a value for A quite clearly, can't I?
27.
Yeah, 27. A is always the first term. R is it's a common ratio, and that's found by dividing one term by its previous term. So it's 9 divided by 27, which is a third, or 3 divided by 9, which again is a third. If that was a third and that wasn't a third, you would not have a geometric sequence going. Now the end there, the end's going to have to stay, because what we want is a rule that's going to enable us to find any term in the sequence, so n stays. And then we substitute a value for n in it's going to be in the second example I'll show you in a minute. So here, having got our parent formula down, we note down the values of the pronumerals of interest. So A is 27, R is
a third.
Yep, it is a third. Let's just write it like that so that we know where everything's coming from. And that's all we need. So the rule for this sequence, this geometric sequence, is 27 times R's a third, and you're going to raise that to the power of n minus 1. That is a solution to that question. We found a rule that describes that sequence of numbers. Okay? Alright, next step is to find the 10th term in the above sequence. So we had the first 3 listed. Now we want to use the rule we found to find any term we want, in this case the 10th term. Okay? So, what we need to do here is recall what the rule was.
Tn.
Equals AR.
No, equals 27 times 1/3
Oh, the one.
to the power of n minus 1.
N minus 1. Sorry, that's a bit messy. So it's 1/3 raised to the power of n minus 1. So to find T10 is a simple matter, really, of simply substituting 10
into
for
n.
n. Yeah. So 1/3 10 minus 1. Okay? Therefore, the 10th term is a very small number. 1/3. Now you've got to be careful when you're raising fractions to powers. If you raise a fraction to a power, you're making use of this index law here. A over m raised to the power of n is equal to a to the power of n over m to the power of n. Okay? Be careful with fractions, just recognise that index law there. Okay, well that's all right because T10 equals 27. 1 to the power of anything is still going to be 1, isn't it? 1 times 1 times 1 times. It's just 1. So that's nice. And that's 3 to the power of 9 like that. And you could go to your calculator at this stage and key that in. Of course, because some of us might have a bit of experience, we'd say, well, just a minute, 27 is 3 to the power of 3, isn't it? It is. And 3 to the power of 3 times 1 is 3 to the power of 3. So really what we've got going is this. And we could simplify that to, we're dividing one number with an index by the same number with another index. So we simply can say this. 3 take 9 is 6. So you can write it like that, negative 6 I should say, or this might appeal to you, might be more intuitive, like so, okay? Either way, we'll go to our calculator and evaluate that number, okay, which I'll allow you to do at your leisure. To be honest, I'm quite happy with that as an answer, okay? I certainly wouldn't want to see it in decimalised form, because that would be not in exact form. We try to present answers in exact form in mathematics as much as possible. Okay, so there are our two first basic examples. I'll ask you to turn off the tape.